I don't think I have permission to share. Can someone? Yeah, okay, let me try again. Okay. There. Okay, I think we're ready. Good. So yeah, the goal is to start talking about variational quantum algorithms, just so that you understand how we look for specific quantum states or probability densities with quantum algorithms. So let's start with a review of last time. So remember that in classical, we have one unit of information, which is the bit, and it can be in either one of two states, 0 or 1, can be on or off. The quantum bit or the qubit can be in a superposition of both states. And something happens with the qubits when they're in superposition, and it's that we cannot predict the result of one experiment. We have to send a lot of experiments and then look at the proportions of the possible results. All the possible results are either 0 or 1. Each one you make a measurement, it's random, and we can only predict probabilities at the end. Okay, and these probabilities depend on how you write down the state of the qubit. So in the quantum computer, we know how to control this because we know the equations for the quantum gates. We know how the qubits start, in which state, and we can look at how the state of a qubit evolves with respect to the operations. We can compute the probabilities depending on these coefficients that are subject to some restrictions because of something that we need that is called unitarity. We have some examples. So the qubit in completely state 0 can be written down as a combination of 0 and 1 as a superposition where you have basically all the electrons on the 0 state. And we also can write down a superposition, like an equal superposition between the two in this way. So you know what, when you square the coefficient, it gives you 1/2. So that's the probability of measuring the state 0 and the state 1. We can have a change of sign that doesn't change the measurement outcome because the sign goes out when you square it or when you take the modulus. But it's also important to know that these signs can arise and that we can use them for computations, like in the case of teleportation. Okay, so let's try some examples. Can you tell me the probabilities for this, for measuring these states? So for the first one, the state is the one state. What's the probability of measuring the state 0? 50? Why? Let me go back. So the formula is here, right? So the probability of measuring the state 0 is the coefficient you have next to the state 0 on the Dirac notation. So if your state of your qubit looks like this, then the coefficient next to it, which is the alpha, when you square it, gives you the probability. And the probability is a number between 0 and 1 in this case. So what is the probability of measuring the state 1 on that state? So I'm not writing down the 0 state because we assume the coefficient is 0. So what will be the probability of measuring state 0? 0. Yes. Yeah, right, because the coefficient of the state 0 is 0 in this, when we write it down like this. What's the probability of measuring the state 1? 1. Okay, so all of the times when you measure this, you will obtain the state 1. Oh, sorry. And for the next one, the second one, what's the probability of measuring state 0? 1/2. And for the state 1, the same. What about the probability of measuring state 1 for the last one? State 1, not state 0. Yeah, 1/9, okay? And the other one, the probability of measuring state 0 for the last one. It's like 4 times 2, 8 over 3, right? Okay, good. So that's the recipe, okay? And this is for just one qubit state. Of course, the notation will change when you have more qubits. What about the X gate? You remember what this does to the 0 state? Yeah, what does that mean? What's the resultant state when you apply the X gate? Yeah, exactly. So instead of having the state 0, you'll have the state 1. And when you apply it to the state 1, what do you get? The 0, right? So you just flip it, the 0 for the 1 and the 1 for the 0. And what will you have if you have a superposition like alpha and beta for the state 0 and the state 1? What happens? So remember, this is linear. What linear means is you get the gate and you apply it to each factor. Okay, now you know how to apply the X gate to the 0 state. Okay, and you know how to apply the X gate to the 1 state. Okay, so you just apply to each one of them. So that means you apply it to the first one, you just push the alpha to the left. And for the other one, you push the beta to the left. Now, it's the same thing as just changing the alpha and the beta from a place, okay? Because you're changing everything that was 1, it changes to 0. Everything that was 0, it changes to 1. Okay, remember the C gate? So on the 0 state, it does nothing, okay? And every time you find the state 1, you flip the sign, okay? So this means the number that is next to it. Remember, inside the cats, this notation for quantum, we only have zeros and ones. All other numbers appear outside, okay? And these are called the amplitudes. So these are the alphas and the betas. Okay, so what would you have if you apply the C on this superposition? Okay, everybody got that? Sure? Okay. Yes, so you just flip the sign of everything that was on the 1 state. Good. Hadamard gate. Hadamard gate produces an equal superposition of 0 and 1. When you apply it to the 0 state, how do you write down that on the Dirac notation? You remember? I'll give you a few seconds. So the answer is, it's an equal superposition. Yeah, when you square 1 over square root of 2, that gives you 1/2. So that means you need 1/2 probability for each one. So you need to use the amplitude, which is the value before you square it. Okay? Good. So when you apply it on the 0 state, it gives you an equal superposition of zeros and ones. What does it happen when you apply it to the 1 state? Yeah, on the 1 state. Okay? Okay. Now, what will you get when you apply it on an equal superposition, so on a general superposition with the alpha and beta as amplitudes? Yeah, so you basically have to write it down, but it's you take the h to the 0 state, you replace it for what you have here at the top, which is 1 over square root of 2, 0 plus 1 over square root of 2, 1. That's for the first factor, okay? Now you have to apply the h on the 1 state. You replace it for the second one, you distribute everything, and the sign comes up as this minus beta there. So that's what you get, okay? You don't have to remember this formula. You just have to remember that when you have the Dirac notation and you have the gates, you just have to apply each gate on each one of the factors, okay? Now, what about in terms of a circuit? Can you tell me the answers, like the state at the end for each one of this? So let's go for the A. What is this plus in a circle? That's the X gate, okay? And I only have 1 qubit. how do qubits, in which state do qubits start? 0. Okay, so for the example A, you start with the 0, you apply an X gate. That gives you which state? 1. Then you apply the X gate again. What do you get? The 0. Okay, good. Now for the B, remember you read from left to right. You start with the state 0. You apply the C gate. What do you get? Same thing. So the state 0. Then you apply the plus gate, the X gate, and you get the state 1. Okay, so nothing weird here, only just ones and zeros. For the C, we start with the state 0, apply the X gate, get 1, then apply the C gate and get -1, the -1 state, or the -1 ket. Okay, what about D? So D will start with 0. You apply the Hadamard, you obtain this equal superposition between 0 and 2 with 1 over square root of 2. Then you apply the NOT gate. And what does the NOT gate does? It's like when you have just one qubit, you have the 0 and the 1 state. You just flip the alpha and the beta. Okay? But after the Hadamard, alpha and beta are the same, are 1 over square root of 2. Okay? So it doesn't matter if you apply a NOT gate after a Hadamard. You obtain exactly the same thing. Okay, so just to repeat, indeed, you start with the 0 state. The H puts it in an equal superposition between 0 and 1. You apply the NOT gate, and it changes the coefficients, but the coefficients are the same. Okay, good. What about E? Okay, you got it? Is just the Hadamard gate applied to the 1 state. So it's an equal superposition, but the sign of the 1 state is minus. Okay, and the last one, what happens when you apply twice the Hadamard gate? Nothing. The same thing. Sorry. Okay, I have 1 vote for superposition. Any other candidates? Probably people in the chat can answer. There's a minus. This one?
Yes.
But you have to apply it twice, right? Okay. What?
Someone says.
Yeah. So how do you know?
Can you go back to
Yeah.
A and the B are 1 over square root of 2.
Mm-hmm.
So on the right side, the alpha minus beta gives 0. The other one should be 1.
Yeah. Mm-hmm. Exactly. Yeah. So basically, he did the math, right? So I know you're trying to do it like graphically. That may not work sometimes. Okay. So you have to write it down. Okay. Good. That's let's say the first tenet of quantum computing. You have to write it down. Okay, let's move on to 2 qubits. Everything good with 1 qubit only? Any questions? Okay, good. So let's move on to 2 qubits. Remember the CNOT gate? So it's a control gate. You start with so the notation we're gonna write down is this CX. We're gonna have 2 indices. So these are going to be either zeros or ones. The C is going to be the control, and the T is going to be the target. Now, inside the state, inside the ket, we're going to have a sequence of zeros and ones all the time. And we label them from right to left. Okay, this is very important to remember. So from right to left means, for example, if the control is the 0 qubit, that means the control qubit inside the ket is the one on the right. Okay, so it's the first one on the right. For example, here. So we apply the C naught gate, and as sub-index, we have 0, 1. That means that the 0 qubit is the control, and the qubit 1 is the target. Now, what's the state of qubit 0? On the first one is 0, okay? And the target qubit is the one on the left. So do we change the qubit on the left, the state, or not? No, because the control is in the 0 state. We only flip it if the control is in the 1 state. So every time you see the control in a 0 state, you do nothing to your qubits, okay? To the states of the qubits. Yes. So you see the CX, and below, like an index, is 0, 1. You will always have two values here, either zeros or ones. They're always going to be different. One of them is going to be 0, the other one is going to be 1, and they represent the qubits that you apply this C naught. So in this case, let's say you have only.
So the C and the T.
Yes. Yes. So if you have more than 2 qubits, these indices can be 0, 1, or 2, or 3, or 4, depending on how many qubits you have. In this case, I'm assuming I only have 2 qubits, the qubit 0 and the qubit 1. We start labeling the qubits from 0 and from the right, okay, inside the ket. So what this notation means is CX sub 0, 1. Now the order means the 0 is the control and the 1 is the target. Now we are applying it to this ket that has 0, 0. Which one is the control qubit?
Just precise like the indices of
The indices are from left to right, but inside the ket,
okay.
it's the other way around. Yes. Yes.
Maybe I'm the only one that can just move forward, but I still don't, I think it's like, I'm still thinking about the little tools that you had online the last time with the 2 qubits that were superposed, like.
Yeah.
So, what's the, anyway, I can just go see it.
No, it's okay. So let me see, where did I have a circuit? Yeah, maybe I can go for a circuit. That's better. Actually, I'm gonna open the Quantum Composer. Can you see my screen? Oh, no, you can't. Okay. Yeah. Okay, so here's the Composer. Okay, can you all see this? Okay, good. Now, here I start with 2 qubits on 0 state, each one of them. Here down below, you can see the states of these bars represent the amplitudes. So since both qubits are state 0, I only have amplitude 1 on the 0, 0 state, and I have 0 amplitude on the others. What will happen if I apply a C naught that is controlled by the 0 qubit? So that means when you look at here at the bottom, the control qubit is the one on the right. Okay. So what happens when I apply the C naught here? Nothing. Exactly. Okay. So because the control qubit is on the state 0. Yeah. Yeah, exactly. So when you go back. Yeah, so in this case, what will be the ket after you apply the C naught on this 0, 0 state? Yeah. The next one? Sorry? Yeah, so if I go for the, which one was it? Okay, I need to twist it, right? So if I go here for the, okay, now it's the other way around, and I get the same one. Okay? Good. Now, let me go back to the presentation, which is there. Okay. So the first one is the 0, 0, because we're controlling with the qubit on the right, which is 0. The second one, the control qubit, is the one on the left. Okay? So that means when I apply to these two, the control is the one on the left, which is 0. So I do nothing. Okay. What about the next one? Whoops. Okay, what about the next one? Which one is the control qubit? Is the first one on the indices, which is the 0. Now I go for my qubits. What's the state of qubit 0? It's 1, because it's the one on the right. So I flip the one on the left, which is the control, the target. Okay. And for the next one, which one is the control? The one on the right? No, the one on the left. Because the control for the last one, the first index is the 1, which is the control. The other one is the target. Okay?
The index of this EX, I was trying to interpret it as states of quantum, but it's not that, it's just which one is the control.
Yeah, which one is the control and which one is the target? Yeah. So this is confusing because we have 2 qubits. Yes, exactly. Okay. But if you have more qubits, these numbers can be any one of the qubits. Yeah.
It'd be nice if it's like circuits.
Yeah, we have a part with the colors actually. When you add more qubits, because it's going to get more confusing. But yeah, okay. So okay, but the thing is, you can do it if you remember the formula, right? So the formula is this. And if you ever have to write it down, you just go look at the slides, write down the formula, figure out which one is control, which one is the target, and you do it by hand. Okay, good. Now, can be confusing, but you should be able to follow it's just a recipe. Okay, good. Now, everything else we're gonna do, we will not need to do all of this by detail. Okay, I just want you to know that you can do it. It's not that hard. Good. So here we have more examples. I'm not gonna put you through it. So how in the world did we come up with all of this? We look at some mathematics that is called linear algebra. And here we have things called vectors. Vectors are lists of numbers. So for example, this, so you can have 1, 0, 0, 0, that's a vector. The other one, you can have minus pi over 2, and the other coordinate can be 214.43. So that's a 2-dimensional vector. You call the dimension of the vector the number of elements that you have on the list. You can add any amount of numbers that you want to the lists. And you can perform operations on these things. So for example, if you have a 3-dimensional vector and you want to multiply by a number, what you do is you multiply all the elements in this list by this number. You can add these vectors if they have the same size. Okay, so if they have the same size, that means you have one element on one of these vectors corresponding to one element in the other vector. You just add them. Okay, because they are numbers, you can add numbers. Now, if you do it like we call it coordinate-wise or element-wise, you can add vectors of the same size. And it is not allowed to add vectors of different sizes. So you don't do this. It's not well defined. So what do we do with this? So the thing about the Dirac notation is it's a notation for vectors that is easier to write down. Okay. So here, the 0 state, we replace it with this vector, 1, 0. And the 1 state, we replace it with the 0, 1 state. So what that means is the quantum computer is not working with zeros and ones. It's working with vectors. Okay, so when we say we have a superposition of 0 and 1, what it means is we have a combination of these two vectors. Okay, it's not 0, it's not 1 as you know it. We just use zeros and ones because it's easier to write it down. But what it means is we have a vector. And the alpha and the beta are numbers multiplying these vectors. And these are vectors of the same size. So that means we can add them. Okay, so we can write this direct notation, we can write it down in a vector like this. Okay, so for the 0 state, we have 1 on the first coordinate. 1 times alpha gives you alpha. And the other coordinate is 0. That's for the first factor. For the other one, you have a beta on the second factor. You add them, and you have alpha on the first factor, beta on the second one. And we have this condition of normalization that alpha squared plus beta squared gives you 1. But the thing is, you work around with vectors all the time. This is the right way to interpret the quantum computations. Now, how do we operate on vectors? So vectors are arrays, lists of numbers. We would like to transform them. Like, for example, we have a qubit in this alpha beta superposition. We would like to act on it and obtain another vector, like another qubit, right? So this will be the notion of a gate. So the gate, again, we have a mathematical description, and that's called a matrix. So a matrix will look like this, and it's just a table of numbers, okay? So one is lists of numbers, and the others are tables of numbers. And again, if your tables have the same dimensions, now you have 2 dimensions, you have width and you have height. If these are the same, you can add them because you have the same shape on your matrices. You just add them coordinate-wise, element-wise. So these have to be the same thing as this. In this case, I just put 2 by 2. But if this were 2 by 3 and 2 by 3, you can do it. And the result has the exact same dimension because you just add element-wise. You don't add dimensions. And you can add on vectors in this way. So I'm going to show you the formula. It's not necessary that you remember it. This is just so you know that this can be done and that it's easy to do. So first, let's say you have a matrix A, B, C, D, and you want to apply it on a vector X, Y. And this is going to be a qubit operation, basically. The way you do it is, first you need the same number of columns on your matrix, and you need the same number, that you need to be the same as the number of rows in your vector, of the number of elements in your vector. Because you will get the first one here, which is A, multiply it by X, and that's your first factor here. And to that, you add the next one. So this is B times Y. Okay, so you can see, you take the first row, and you multiply that element-wise for the elements on the vector, and then you add each one of them. Okay, so you can follow this recipe for bigger matrices, bigger vectors, and that's how you obtain all of the others. So for the next term, you proceed with the next row. So you do Cx, and that gives you the first factor. Then you do dy, that gives you the next factor, and that's it.
So the size.
Mhm.
Qubits you have, the bigger the matrix.
Yeah. Exactly. But we're going to use another trick, which is called the tensor product, to deal with these matrices, because they will get bigger. Yeah. So what about this one? Can you do this product? Yeah.
Okay. So qubit works with a vectorial base. Depending on the number of qubits, the dimension of the vector base is 2 exposed NV, NV being the number of qubits.
Yes. Yes, we're going to get there. Okay, so what about this one? The bottom right. What will be the result? So the what?
Error.
Error, exactly. This is not well defined because the number of columns in your matrix is not the exact is not exactly the number of elements in your vector. Okay, good. Okay, now let's go about the qubits. Let's put this into practice. Remember, the 0 state is the 1, 0 vector. The 1 state is the 0, 1 vector. The X gate representation is like this. So it's this matrix, which is 2 by 2, because you act on 1 qubit. And so that means you have a 2 by 2 matrix, because you will apply it on a 2-dimensional vector, and you will end up with a 2-dimensional vector. Now, the X gate flips the states from the 0 state to the 1 state. So what would you do in terms of matrices and vectors if you have the matrix representation? So you replace the matrices and the vectors, you do the computations. So in this case, you go for the first row of the X gate, and you multiply it element-wise by the elements of the vector. So that gives you 0 at the top, okay? So here are the factors. For the next one, you go and do the same, okay? But now you have 1 times 1 plus 0 times 0. So that means at the bottom, you get 1, and at the top, you get 0. And this is exactly the vector representation of the state 1, okay? So what will happen when you apply it on the 1 state? You get this. You apply the first one, then you get 0 times 0 plus 1 times 1. So at the top, you will get a 1. And at the bottom, you have 1 times 0, 0. 0 times 1 is 0. So you get a 0 in the second coordinate. And that is nothing more than just the 0 state. Okay? Good. And we just recovered the equations that we wanted, which are these ones. And these ones. Okay? And we can write down like just the superposition of these vectors and do the computations on this general alpha and beta, and you will get the same thing. So yeah, here you can see if you apply it. So for the first one, you get beta because 0 times alpha is 0, 1 times beta is beta. And that's how you do it. So this is what's behind curtains for the X gate. This is what's actually happening. For the Hadamard gate, we have something a little bit more complicated because we have this 1 over square root of 2. But we can use this thing that we can multiply numbers for a matrix, and we just do it like element-wise, just as we did with vectors. And so this is what we're supposed to get, right? So we send the 0 state to this equal superposition, and this 1 state to this other superposition. And the matrix is this one on the right, okay? So it's, you just put everything has 1 over square root of 2, so you just put it outside. That means you have to multiply each one of the elements by this number. And if I read it from left to right and top to bottom, I have 1, 1, 1 minus 1. Now, what will that look in the matrix vector representation? So you will have something like this. Forget about the number. You can do numbers at the very end. That's one of the beauties of linear algebra. So you just work around with the matrix and the vector. What will you get here at the first one? So you have to do this. So 1 times 1 gives you 1 plus 1 times 0, which is going to be 0. And you end up with this vector. Okay. Now, what is this vector? Okay. If you look at this vector, this is when you add the 0 and the 1 states, it gives you this vector. Okay. And the 1 over square root of 2 comes from the condition that you have an equal superposition between the two. So it's this thing written down in just terms of the vectors. Okay. Because here inside this superposition, where I'm putting the cursor, you can see the 0 state plus the 1 state. If you add these two vectors, you get the 1, 1 vector. Okay, so it's exactly what we have here. And what about the 1 state? Then you can do it, and you will see that you will have a -1 surviving here at the bottom and a 1 at the top. And that corresponds to the 0 state minus the 1 state. Okay? Good. And we have other type of gates that we'll be using for the next part of the workshop. But I'm not gonna get into the details, but the thing is you can write down the equations, the form of the matrices, you can multiply by these vectors and you obtain the right description in terms of either the vector representation or the Dirac notation. And they mean exactly the same thing. Okay, now this gate has its own inverse. You can add an angle there. It's called Ry because qubits are going to be like, you can represent them by vectors in a three-dimensional space. You have X, Y, and Z axis. The Ry means a rotation with respect to the Y axis. We also have Rx and Rc. You can write down what this does to each one of the states. Okay, now, 2 qubits. Okay, now we've seen what happens behind 1 qubits and the states, how we write them down, how they're really vectors, how gates are really matrices. Okay, but what happens to those matrices and those vectors when we add qubits? Like, how do we manage multiple qubits in this vector notation or the Dirac notation? How do we make it compatible? So we write it down in terms of something that is called a basis in terms of linear algebra. And what that means, the basis is all the possible results from your measurements. Now, if you have 2 qubits in superposition, all the possible results are 0, 0, 0, 1, 1, 0, 1, 1. You only have 4. That's your basis, okay? So that means a vector here is going to have to be written down like this. So we call this a linear combination of the basis. We have coefficients in each one of these basis vectors. And we obtain the probability of each one of them by taking the square of the modulus of each one of the factors corresponding to each one of the possible measurements. Okay, so that means if I have alpha is equal to 0, I cannot obtain the 0, 0 state as a result of measurements. Okay, I can obtain 0, 1, 1, 0, and 1, 1, but not the 0, 0 state if alpha is equal to 0. Okay, so I can cancel some of this if I put the coefficients to 0. But the thing is, I can still write it down as a combination of the others by adding zeros to the states that do not appear here. So we can write it down like this. So the first one will be like, this is an equal superposition of the 2 qubits. So you have 25 probability, like 0.25 or 1/4 probability of having each one of the possible measurement outcomes. And again, to obtain these probabilities, you have to put 2 qubits in superposition, do the measurement, register what you obtain, and then put the qubits again in superposition, take a measurement, register what you get several times, you average, that gives you probabilities. Okay, good. Now, the thing with vectors and qubits is that when we add another qubit, we need to put an operation that is called the tensor product. Now, don't ask me why, because nobody knows why. And the thing is that apparently this is what nature does. Okay, so apparently nature, when you put the 2 quantum systems in interaction, what it's doing is taking the vector representation of one system, the vector representation of the other, and it's doing a tensor product. Okay, so I don't know, maybe you should ask a priest or something, but not me. So, okay, now the tensor product works like this. So you have 2 vectors. Let's say I'm putting colors here and figures just to make it more visual. So the first one is in this red, blue state, and the other one is in this triangle, square state. And you expand this to just so that you have the multiplication of the first one on the first element times the 2 elements on the other. So here the red is going to multiply completely the vector on the right, which is the triangle square. And this is just an element-wise, these are going to be numbers instead of colors and figures. And how do you do multiplication of a number and a vector? You do it element-wise. So we represent that here by coloring. So on the first coordinate, you get a red triangle because you have the red multiplying the triangle. And the second one, you have a red square because you have the red multiplying the square. And for the others, you have the same thing. So again, this is a recipe. So if you have the vector representations, you can just write it down and do it by yourselves. Okay. Now, careful, because I don't know if you remember this thing that they teach you in high school, that the order of the factors does not alter the product, something like that. So you have two numbers, you multiply them, it's the same thing as you twist them and you multiply them. That is not true here. Okay. And this is how nature is doing things, and this actually happens. So you have to be careful with the order, because let's twist it and see what happens. Okay. So now we have the vector with the figures on the left and the colors on the right. On the step on the middle, we have to multiply the triangle by the red and the blue. And in the bottom, we have the square multiplying the red and the blue. When we color them, we see that at the end, we obtain a different vector than the one on the left. Okay? So we need to look at the order of these vectors if we really want to get the state at the end, the right state. Okay, let's do a first example. We have qubits in state 0. How do we represent it as a vector? We do it like this. So we do the tensor product of the 0 state and the 0 state. Now, the vector representation is 1, 0 for each one of these vectors. Now, I changed the big parentheses for this bracket. It means exactly the same thing. And I'm keeping with the colors so that you can follow the recipe on top. But it's basically you take the first coordinate on the first one, multiply by each one of the coordinates of the vector on the second factor on the tensor product. And the same thing for the other factor of the first tensor factor. Okay. So what that means is you follow this recipe. So 1 times 1, 0 gives you 1, 0. And at the bottom, you have 0 times 1 and 0 times 0. And these are just zeros. And this is, by definition, what we mean by this 0, 0 state. Okay, so this is, when we write the diskette with 0, 0, what is behind curtains, what is actually happening is this tensor product.
So if I look at the color,
Yeah.
the red 0 will be on the right.
Which one?
If I look at the red 0 here,
Mm-hmm.
in the final ket, it will be completely on the right. The final ket.
This.
Yes.
Yeah.
Okay.
Yeah, actually
So it
this.
preserves the order.
Yeah, exactly. Yeah. So actually these three symbols that I'm drawing down here at the bottom, they mean exactly the same thing. And it's tensor product. Okay. So when we did this computation of how we compute entanglement, how we produce entanglement, what we were doing is applying gates on each one of these tensor factors. So this concatenation, what this concatenation of the state means is tensor product. Okay. Okay, good. Now, what about the other states that we already know? What is the vector representation? Can you do it? You have 1 minute. Okay, so you have to obtain these states. I'm going to go back to this recipe so that you can look at it while you compute. Where is this? There. Okay. Okay. So this is what you have to do. Okay, for the other states. So you, instead of having the 1, 0 and the 1, 0 on this tensor product, you need the other combinations. Yes, there. Finish? So it gets can get complicated if you're only doing zeros and ones. So, but what you should obtain at the end for the 1, 1, you have a 1 on the last coordinate only, right? And again, you just write down the formulas for the tensor product. You can do it as homework, just to remember that you can do this if you look at the formulas on the presentation. Okay, so that's what happens with multiple qubits. And so now when we translate this to the Dirac notation, so again, the Dirac notation, what does it mean? So we have all the kets that corresponds to the different outcomes of measurements, right? So qubits can be zeros and ones. We have 2 qubits. All the possible states are all the possible combinations of zeros and ones. And we have alpha, beta, gamma, and delta as amplitudes on these basis vectors. And these are getting replaced by these vectors, okay? So that means that when you multiply the first one by alpha, what you obtain is on the first coordinate, you get an alpha. On the second coordinate, you get a beta, and so on and so forth, okay? Now, this is because when we do these tensor products of the 0, 1 vectors, what we obtain is basis of higher dimensional vector spaces. Okay, so what this means is that every vector is a combination of these 4 vectors when you talk about 2 qubits. If you go to 3 qubits, you're going to have bigger vectors, but you're still going to have a basis. So every vector is going to be a combination of this. Okay? So that's how you represent in terms of the Dirac notation. You can represent all of the vectors that the quantum computer can represent. Okay, now that's for 2 qubits. What happens when we add more qubits? Okay, so we have 1 qubit. We can put the first one in the Dirac or the vector notation. We can apply these gates. Probably you don't know what the S dagger does. It doesn't matter. But if you know the matrix, you can do it. Okay, and you will obtain a 2-dimensional vector. If you have 2, you can write down the matrices. You will have to do something called a tensor product of matrices, which doesn't matter for now, but it's kind of the same recipe as for the vectors. Or you can apply these matrices on each one of the elements of the tensor product. Okay, so we're going to look at that after. But this, you're going to get a tensor product of 2 qubits. Okay, so the first qubit, it's on a state alpha beta, and the second qubit is on a state gamma delta. You do this tensor product and you obtain a 4-dimensional vector. What happens if you have 3? Then you have 3 tensor products, okay? You have a tensor product of 3 vectors. This will give you an 8-dimensional vector. Okay, so every time you add a qubit, you doubled the number of elements. Okay, this is what if you write down the tensor product for the 3 qubits, you're gonna realize that every time you add a tensor product by 2-dimensional vector, you double the size of the vector. What about 4? You will get 16. Okay, so every time you have two vectors of dimension 2 to the n. Okay, and this grows, this is what we call exponential growth. If you add 300 qubits, you will not be able to write this down even if you use 1 atom per entry of this vector. So that's why we need that's why we think quantum computers can be useful, because we can access these kind of vectors. Okay, good. And we would like to do computations with them. Okay, what about 2-qubit gates? You can write down matrices. So these are 4-dimensional vectors. You will get a 4x4 matrix in this case. You can write down the matrix, for example, for the C0. We know what it does for each one of these. You can try to do it as a homework if you feel brave. It will probably not teach you nothing new, so it doesn't really matter. It's just that you know that you can write it down. So in terms of the Dirac notation, and this is interesting, now that we know that what we actually do is apply these quantum gates on each one of these tensor factors. Let's write it down again. So entanglement. We start with the qubits on 0, 0 state. We put the qubit 0 on superposition, which is the qubit on the top. That means the red H on the circuit. So we put, when we act on the qubit 0, what we do is we put an index on the H gate, okay, on the right-hand side here on the Dirac notation. So that's why you see an H sub 0. Now I'm factoring this 0, 0 state into a tensor product of 2, and I'm putting indices corresponding to the index on the tensor product. So that means I need to apply the H0 on the tensor factor that has a 0 as an index. When I do that, I just apply the formula for the H, and then I do tensor product of this. So tensor product is concatenation of the states. I get this value. There's a state, sorry. Then I apply the C0 gate, controlled by the qubit on the right, and I do it linearly. So I do factor by factor. I go for the first one. It does nothing because the control qubit is on the state 0. The other one has the control qubit, which is the one on the right. It has a 1. So that means I need to change the 0 for a 1. And I obtain this state. Okay? And this is exactly what the circuit is doing. And you can write all of this with vectors and matrices, but you will get tired because this can get more complicated. So it's easier to write it down in terms of the Dirac notation. Okay? Cool. What happens with n qubits? So we have a lot of coefficients. When we have n qubits, we have 2 to the n different outcomes of the experiments. Okay, so because each qubit can be in 0 and 1. We know that this is going to be a vector of size 2 to the n, and each one of these represent a basis of the vector space because it's tensor products of bases of zeros and ones. So that means we can have 2 to the n different outcomes when we measure n qubits. Okay, so that means if we have 2 to the 300, 300 qubits, we have 2 to the 300 different outcomes. So that means that even if we have a quantum computer with 300 qubits, and we can work around with these vectors of the size of bigger size than there are atoms in the universe, we cannot save these computations because we don't have space to save them. You see the problem? So we need to do something very clever to use these computations. Okay, it's not straightforward. It's not easy. Okay. Good. What about a break after showing you these ugly formulas? But the thing is, you can write it down and you can do computations with this. Okay, and the next part of the presentation, I'm going to move to now variational algorithms and how we search for quantum states by moving some parameters. Okay. Okay, now when you write down a circuit, what this actually means is all of these things in the middle, this actually represents a matrix, which is not only 2 to the n, but 2 to the n by 2 to the n. Okay, so the elements in this matrix are way more than the elements on the vector. Okay. Good. What time is it? Okay, let's just try to follow what happens with measurements now in terms of the probabilities. No, you know what? I think we can have a break here. Yeah, let's have a 10-minute break because might need a coffee and you might need a break. So if you have any questions in the meantime, I'll probably go get a coffee if someone can tell me where I can get a coffee and or a vending machine or something.
I think there's a vending machine downstairs.
Ça dépend qu'il y a une machine.
Hey, yeah, so to share the animations from the presentations, I can't unless you have a Mac because we're using Keynote. So animations will not show on your PDFs, but I think you have access to the recording, so that should be fine.
Je préfère le dire. Si on voit que c'est des corrections mineures, je regarde parce que quand même le mieux, c'est il me semble que parce qu'en fait, il expliquait qu'au directeur qu'à Laval, j'ai vu que je faisais aussi j'avais autre chose qui faisait que je pouvais pas. La moitié de la session, tu peux ça.
C'est normal. J'ai écrit mes 3 semaines pour pouvoir faire ça ça va être avec les seniors. Je pense.
Okay, so I think we can continue. Maybe I can. Working? Hello. Okay. Okay, so we were discussing that when we write down an n-qubit quantum state, we get a vector with all the possible outcomes of the measurement. If we have a lot of qubits like we do today, or in the near future, it will not be able to store all these possible measurements. So we need a clever way of dealing with this. And when you have n qubits, then you end up with this notation. So this will be the general notation for n qubit states. These gates on the circuit, this will be represented by a big matrix, 2 by 2, 2 to the n by 2 to the n. So it's the matrix is even bigger than this vector. And how do we obtain information from these computations? And we do it by doing what we call quantum measurements in terms of quantum observables. Now, quantum observables are a type of matrix that has some properties, and I'm going to tell you how it works. Okay. Now, let's go back to 1 qubit. Okay, so not tensor products, just 2-dimensional vectors, and let's start with the 0 state. What happens when I measure the 0 state? I can only obtain 0. Okay, because we know the state. So we know the direct notation for this. So as an output, I run the circuit, I measure it, I get 0 again and again and again. I can only obtain 0 there. Okay, what happens if I apply a next gate? So this will produce the 1 state. I measure it and I'll obtain the 1 state all the time. Now, what happens with the superposition? I apply the Hadamard gate to the 0 state. I obtain this equal superposition that is usually called also the plus state, so the plus ket. And what it means is just you're defining this symbol as being this superposition. So that's exactly what this symbol means. And when you do the measurement, what do you obtain on the first one? You don't know, okay? So it's going to be either 0 or 1. And the second one, same thing, okay? But you repeat it, and approximately 50% of the times you get 0, 50% of the times you get 1. What happens if you have 2 qubits in superposition? Well, what's actually happening is this. So you have tensor product of 2 qubits in superposition. You write it down, you obtain actually this expression. So that means that you have 1/4 probabilities of measuring each one of the states. So what do you obtain when you do one measurement? You don't know, okay, but you obtain one combination or the other. 1 0 0 1 1 1 0 0. Doesn't matter. You will obtain this. You repeat it several times. You do averages. You get 25% of the times each one of the states, or something very close to 25%, depending on how many times you perform this experiment. What about this state? So we did the math. The last actually we did it today too. So the state that we get is this one, the 0 0 plus 1 1. So that means when I measure it one time, what can I obtain? Yeah. Okay, so I take one or the other, 0 0 1 1 0 0 in a random way. Okay, but I always obtain 0 0 or 1 1. I cannot obtain the others. Okay, now how do we get information from these kind of measurements if I cannot have access to this quantum state? Because actually we don't have access to this superposition. We don't know how to see it. We can only see zeros and ones and probabilities. Okay, so we need a clever way to see what's happening to this qubit, to the computations, and that's via this expected value. Okay, français on dit valeur moyenne. It's like an average value too. And it's basically you average these things, but it depends on something called a quantum observable. Okay. Now, quantum observables are, it's for now, it will always be the C operator. Now, how does that work? It's technical. You don't have to remember the whole story as long as you understand each one of the pieces. So you get your observable, in this case is the C. You apply it to each one of the states. So the 0 and the 1 state. This is just on one qubit. And you see that when you apply it on the 0 state, you get a +1 as a factor. You apply it on the 1 state, you get -1 as a factor. And this observable is going to replace on these zeros and ones, you're going to replace for this plus or -1. So these are called eigenvalues. So we replace these measurements for the eigenvalues of the observable, which are this, and you will have a list of numbers like this. So instead of having the 1, you look for what the C does to the 1 state. So you get a -1. Okay, so instead of having a 1 here at the top, you will get a -1 here at the bottom. For the 0, you go for the 0 state. What does your observable does to the 0 state? It has a 1 as a coefficient, and that's the coefficient you put instead of the 0. Now, you don't have to remember this whole story. You just have to remember that it can be done. And you take the average of this. Okay, and we denote that by this notation. So it's basically, so you have the dual of a cat, which is this symbol but twisted. Instead of being a cat, we call it a bra because it's a bracket. So we have a bra plus, and then the C, which is the measurement, the observable operator. And then we have also the plus state. Now, all of this, what actually means is products of vectors and matrices. Okay, I'm not going to write it down because it's going to be a mess, but that's what it means. And we have mathematical results, mathematical result that says that this thing can be calculated from the measurements that we get. Okay, so we don't have to get the complete measurements of all the possible results. With just a few, we can approximate this expected value. Okay, and we do it like this. So we look at these eigenvalues, we replace the ones and the zeros that we obtained for these plus and minus ones, and we take the average of this. Okay, that's the expected value. Now, for this many, we obtain an average of minus 0.166. But if we keep on producing more and more and more, we will get closer to the 0. Okay, on this average. So if I add more ones and zeros, I will replace that for the eigenvalues, which are ones and minus ones, and I will get something more closer to 0. Okay. Good. Now, if I measure this on one of the initial states, what do I do? So let me go back here. So in the first one, I get only zeros. Okay, so this is the zero state. What happens when I apply the C to the zero state? It gets a +1 on the zero state. Okay, so I should replace every time I have a zero for a 1. What's the average of having only ones? It's 1. Okay. So, and what will be the other one? If I start with the 1 state and have only ones, I replace it for the eigenvalue, I get only -1s. What's the average of only -1s? It's -1. Okay, it's the same thing. So let me go here. Okay. So it's the same recipe. We can do it on any state. Here we did it on a superposition. We can do it on the 0 state or the 1 state or any superposition. The recipe is exactly the same. And so here is on the left-hand side, we have what will be this expected value on the 0 state. On the right-hand side, what will be the expected value on the 1 state. And these are the bounds. Okay, so the expected value for any state when we measure the C observable is going to be between -1 and 1. Okay, good. Now, and these values, we can measure them from a few probabilities. So these probabilities will approximate this expected value, and we can use this number, which is between -1 and 1, to make something like deciding on a classification problem in machine learning, which is what this project is about. So it's we will be using expected values to predict labels of a data set. Okay, yeah.
Just one question. Why, if I look at the bottom circuits,
Yeah.
why the Z doesn't show units?
In your circuit?
Yeah,
Because this is not the result of the circuit. So
okay.
the expected value measures something else, measures the observable. Okay, so this C, this is what you're measuring. You can change the C for the X and you can measure the X. And you will need to do the same computations for the 0 state, the 1 state. You will obtain other type of eigenvalues. And you replace this, you will do another average. And that way you can measure the X. There's another one that is called the Y. You can do the same thing.
Okay.
Okay. So yeah. So if you stick to the C, this is what happens.
Okay.
Is that good enough? Okay. Good. So this is the clever way of obtaining information from quantum states. Now we have to extend this to multiple qubits. I'm not going to do it, obviously, because actually when we do quantum machine learning, we can do this in a black box, more or less way. So just that you know that the output of the quantum computer can be these probabilities. We can transform these probabilities into these expected values of observables. So this will give us some numbers there that we can use to make another thing. Okay, like make a decision on a problem or model the energy of a molecule. And this is how it works. So you have your circuit, you end up with the state, you perform the measurements, you will obtain some values, you will get the probabilities, and with these probabilities, you will compute the expected value of an observable. That's the story. Okay, now, what do you do? So you have this very big space of n qubits. Let's say you have 300 qubits. You write it down like this. This is good. If you write down this sum, you're going to have 2 to the n terms. Okay, so 2 to the 300 terms. You cannot write that down. But you can control these amplitudes via the quantum gates. So one of the quantum gates I showed you had an angle which corresponded to a rotation on the y-axis. You can have a rotations under the x-axis and the z-axis, and these are called parameterized gates. So you can parameterize how much you rotate in terms of one axis for each one of the qubits, and it gives you degrees of freedom to explore inside this space. So you will not explore the whole space, but you can explore like a tiny amount of it, which corresponds to the degrees of freedom that you have is 2 times 2 to the n minus 2. And we have some red words there that this is what how you count these degrees of freedom, but you can just believe that this is a formula that gives you the degrees of freedom to explore this space. And the idea is to produce a state that is parameterized. What that means is you have some parameters that are going to control your quantum state. How do you do it? With parameterized gates. And you can start either with the 0, 0 state, so all your qubits on the 0 state. Then you add this u hat of theta. What this means is you have a lot of matrices that has parameters of rotations. And this bold face theta, what it means is you have several parameters. It's a vector of parameters. Or you can act over another state that you prepared somehow. So for example, let's say we have a 2-qubit system and we want to parameterize it. So in this case, we can prepare this one. So what it says is you have this cosine and this e to the I phi. This is called a global phase. So you don't know about this. So when you take e to the I phi, you take the modulus, this is equal to 1. So in terms of measurements of this thing, it doesn't matter, but it will matter in terms of other computations. Just as the -1 for the C, this was important for teleportation. So these numbers will be important too. So in this case, this will add a degree of freedom inside this huge space of the qubit space that we call the Hilbert space. And the way we write it down is, so the phi i's in this sum at the bottom right are the basis states of depending on the amount of qubits that you have. Now, the parameterized state that we built here at the top, it acts on 2 qubits only because the kets have only 2 terms. The basis has 4 elements. And these coefficients are the coefficients here on this vector on the left. Okay? So it's just a way of writing down a parameterized circuit. And we can write it down also in terms of a circuit. Now, the math is on the right-hand side. You can do it as a homework. You can write down the expressions of these matrices that I gave you before and just apply them. And you will end up with exactly this state that you want. So you can prepare these parameterized states with quantum circuits. Okay, so when we evaluate an observable on these parameterized states, we are going to obtain a parameterized expected value. So the expected value will depend on these parameters. And we can compute derivatives, whatever that means, with respect to these parameters, and we can do optimization. Okay, so we can tune these parameters and say, okay, I'm going to move this one higher, this one lower, with an automated algorithm that allows me to get these expected values somewhere. Okay? And this is what the applications are all about. So we found a parameterized state, we measure an observable, we obtain a parameterized expected value, and we do optimization. We tune this theta, we move this theta in a way so that this expected value goes to between this -1 and 1, and we do decisions based on that. Okay, so the whole picture is this. You have a circuit, you prepare a state, you measure an observable, you compute the expected value, and you do something with the expected value. You have a parameterized state, you have some parameters that help you move inside this space in a smaller space, inside the Hilbert space. And then you can use how the expected value will move with respect to these parameters to do something else. For example, okay, quantum chemistry. Now, in chemistry, you would like to understand reactions and predict what these reactions will get. Is that correct? Good. Now, that depends on the energy of your molecules. You have 3 molecules, let's say AA, BB, and AB. And we can compute something called like the ground state. So this is the lowest energy level possible of each molecule. Then we can know how these molecules will react. So for example, if I compute the energy of AA, BB, and AB, and I compare them, and I get that AB is the one with the lowest energy, then I know that the first two will react to produce the third one. And it all depends on a measurement of energy. Now, the energy operator, it's an observable, and we can build this in a quantum computer. Okay? Now, the way it works is in chemistry, you can write down something called the Hamiltonian of a molecule. The Hamiltonian, it's a big matrix, basically. And you solve an equation that gives you the eigenvalues of this thing. Now, the eigenvalues is what you need to do measurements, right? And on a quantum computer, you just replace the ones and zeros for the eigenvalues, and then you can compute these expected values. But now on a quantum computer, what we do is we prepare a parameterized quantum state, and we optimize with respect to these parameters to obtain the lowest possible energy. So this expected value, this will be an approximation of the energy. And we can do this for each one of the molecules. So if we have a sequence of molecules, we compute the energy for each one of them. We know how they will react. And this is apparently good for chemistry. Okay. And here we have an example for the H2 molecule. So you write down something called the fermionic Hamiltonian, which looks like this. But the idea is that all these, so these I, C, X, Y, these are matrices. If they're concatenated, this means tensor product of matrices. And these coefficients at H sub something of R, they depend on the distance between these two H atoms and some other thing that comes from chemistry and the quantum physics of these atoms, which I think it's the orbitals, right, Nicola? Yeah, okay, so this comes from information from the orbitals. And this is the observable you would like to measure on a quantum state. So what you do is you create a parameterized state with a parameterized circuit, and you evaluate each one of these observables, and then you compute the expected value of the energy. And here is a result from a paper for this H2 molecule. Now, the green curve, this is the best classical approximation. So that means you use a classical computer to approximate the energy of the molecule. The gray curve, this is the exact solution. So this means you solve the equations, and this is what you should get. This is what the theory says. And the blue points, this is with VQE. VQE is variational quantum eigensolver. It's a variational algorithm that allows you to approximate energies of molecules, for example. And you can see that the blue points, they all like very, very, very close to the exact solution. So this is one of the things where quantum computers will excel, because each qubit is a quantum object. And so these electrons on orbitals. And this is exactly what we can measure, okay, on quantum computers. So molecule simulation, energy approximation, it's one of my favorite applications of chemistry, because you cannot compute this classically, because molecules, you will have a lot of things, a lot of atoms, a lot of molecules combining. For example, here, so for the H2 molecules, you need 4 orbitals, and you need 1 qubit per orbital. Okay, so that means the state vector will be 2 to the 4, which is 16. Okay, you can do it on a classical computer exactly with the quantum algorithm on a simulator. But what about the others? So H2O has 14 orbitals. The state vector will be of size 16,000, a little bit more than that. And the very one at the bottom, this is caffeine. There is no way you can do this on a classical computer, or if you can, it's gonna take a while. But you can do it on a quantum computer with 160 qubits. Okay. So, and yeah, so here at the right, it says that with a good computer at your lab, you can do the NH3 simulation. This is a classical computer. But the next one, C2H2, you need like a 65,000 good CPUs. So you need a national level supercomputer to compute this for a long time. Okay? So this is one of the applications of variational quantum algorithms. You can approximate energies of molecules. Okay, now we have other type of problems like combinatorial optimization. Now, combinatorial optimization means you have a graph and you have some routes, okay? Now here, well, routes or edges connecting the nodes. And what you would like to do is partition this. Actually, yeah, okay, I don't have this story here. We have a workshop precisely on combinatorial optimization, and we have a story with the superheroes and missions. And I'm not sure I'm gonna have time to go through all of that. But here, what basically is you have to separate the nodes into two teams. Okay. Now you do that with by referring to a basis state and the basis states are only zeros and ones. So if the state of something like this is 0, 1, 1, 0, 0, now you can see that the pink node and the blue node are ones. That means they correspond to one of the teams. And all of the others are zeros, so that means they correspond to the other team. And what you can do is you can build an observable so that when you measure the expected value, you will get a gain of this problem that is called max cut. Okay, max cut means you separate this into two teams, and then you look at the edges joining the different teams, and you cut these edges. And you would like to look for the optimal way to do this is separate them in a way so that when you cut the most edges. Okay, you can try all of the possibilities, and if you have enough nodes, you will never end. Okay, this will take you more than the age of the universe, something like that. But you can do this with a quantum computer. So on a quantum computer, you prepare a state that is going to be a superposition of all the possible solutions, and you measure this this gain with this observable, which is going to be an expected value computation. And you can obtain some kind of gain for a specific decision on this problem. But then what you do, oh yeah, you can explicitly compute the gain for in these cases. And then what you do is you parameterize your circuit. So by adding these parameters in this circuit, you can do optimization over the theta. You do this gradient descent. You can compute the gradient, follow the gradient, find the minimum or the maximum in this case, and you will obtain a solution to this problem that maximizes this gain given by this quantum observable. So again, the story is the same as chemistry. You have an observable, you put a parameterized circuit, and then you measure this expected value, and the expected value has to correlate to something in your experiment. So in this case, you start with all your qubits in superposition. That means, so here at the bottom, you have all the possible measurement outcomes. So if you end up with an equal superposition, what you obtain is the same probability of measuring each one of these states.
Another question.
Yeah.
To go back to the previous, the one before, sorry. So because the max cut problem is a classical problem in graph.
Yeah, it's a combinatorial problem.
So you're trying to segment your graph here in two sets of nodes, right?
Yeah.
So the two sets will be the state where the one will be one set and the zero will be another set.
Yeah.
So you have a lot of combination possible. But there is a mathematical definition for the max cut cost function.
Mm-hmm.
How do you go from that mathematical definition and this G function here?
Yes, that's, I told you that we have a workshop on that.
Yeah.
That's what we do in that workshop. So if you're interested, maybe,
Okay, yes,
maybe we can go over that. But this is exactly, so this game, this is the translation. And you can go over this translation. It will be something like we did in quantum teleportation. We will do it case by case.
Okay.
And you will see that this actually is measuring that expression.
Okay.
But this is a quantum observable. Okay, so
Yeah.
this means we can prepare a circuit and measure this observable there.
So the circuit in fact will the term, but encode the quantum version of your class function.
Yeah.
Something like that? Okay. Okay.
Yeah, exactly. Yeah, your cost function has to be a combination of your prepared state and this observable that you're measuring.
Okay. I see.
Mhm. And that's where it gets technical.
Yeah.
Okay. Okay. Yeah, so, and the idea is this. Okay, so you have a parameterized quantum circuit, hit the one as the bottom left. That depends on some parameters theta. You move these parameters and this will move the superposition in a way. And the gain, the average gain, remember this is an average because this is the expected value, which is obtained as an average. This will move and you try to optimize the average gain, not the gain for each one of the steps, for each one of the solutions. So you will end up now, when you follow the gradient, you optimize these parameters. The optimization will give you different probabilities of measurements. And you hope, and this is actually hope, because it's an optimization problem. You don't know if you're going to end up with the optimal result, but that the ones with the highest probability of being measured are the ones that give you the optimal solutions. Okay. Now, in the workshop we have for QAA, we can do this exactly because we have 1, 2, 3, 4, 5 qubits. We can do all possible combinations. We could put it on a table and look that this algorithm is giving us the optimal values. But of course, since here at the bottom you have all the possible solutions, are all the possible combinations of zeros and ones for your measurements. So if you add more qubits, you have more possible outcomes. Okay, so this is why you need at the end a state that looks like this, that have some peaks in some places and it's very small in the others, because you want the ones that has the higher probability to be your solutions. You have to be able to look at them. So when you prepare this state several times and you measure it, when you can compute the probability of the states, you will be able to see that these correspond to the solutions. These are the ones that with highest probability. So these are two things that you have to match when you look at these optimization problems. You have to be able to encode your solutions. You have to be able to put a gain that correlates with your cost function, with the problem you're trying to optimize, and hope that at the end you obtain a probability distribution like this, so that you can observe it when you do it in the quantum computer. If your probability density does not look like this, and it looks like this is not useful. You will not be able to get information out of this. Okay? And all of this evolution, this is what we call interference. Okay? And that it's also technical. Okay? When we go to machine learning, we're gonna do these kind of things, but in a different way. Okay, so that's for combinatorial optimization. Any questions so far? Comments? No, maybe online. Okay, good. So what now about machine learning? We have some things called kernel methods, and the way the kernel methods work are like this. So you have your data, and let's say you have two classes, and you will have to be able to decide which one of these points correspond to one class or the other. And when you plot it, this is like mixed, so you cannot distinguish between them. So you would like to train a machine learning model, in this case, a kernel method, to distinguish between these two classes. The way you do it in a quantum computer is you do what we call a feature space projection. So we take the data and we put it into a quantum state. So this function, this phi, is taking your data from R to the D. So these are D-dimensional vectors. And you put them into this H. This H is Hilbert space, is qubit space. Okay? So you build a parameterized circuit so that in this bigger space, there's a way to classify the data with something very simple like a plane. So for example, let's say we add a dimension, and now the distribution of the points look like that in Hilbert space. And here you can put a plane that separates the two. Okay? Now, I'm saying a plane because actually this expected value, we can we know that it comes from matrices and vectors. That means this is a linear object, and this is like in a hyperplane in a high dimensional space. So you have to be able to put a decision boundary that is linear to distinguish your data. So now when you have a new point, you will only need to look at this plane if it's on the right-hand side of the plane or on the other side to decide to which class this corresponds to. Yeah, so I'm not gonna get into the details of kernel methods, but the idea is that what you end up doing is you get your data, you put it in this quantum circuit, and then you put a plane to do this to do the decision. Now, the way this is done is like this. So we have different ways of putting data into a quantum state. So for example, if your data is 4-dimensional, so you have 4-dimensional vectors, you can use a parameterized quantum circuit like this one. So these are Rx, Ry, or Rc. It doesn't matter. So let's choose some of them. We use 4 qubits. And these are parameterized gates. Each one of them has an angle. And we replace the angle by the coordinates of this vector of your data. So in this way, you obtain a circuit that applies gates that depend on your data. So you're encoding your data as a quantum state on your circuits, on your qubits. There's another way to do it that is called amplitude encoding. So the one at the top is called angle encoding because these gates are rotation gates by an angle. So you put the data as an angle on in these rotations. The amplitude encoding means you put your data as amplitudes of your Dirac notation. So the alphas and the betas are going to correspond to the elements on your data vector. So, and the way you do this, it's complicated because you have to construct a circuit that builds a specific superposition so that these factors, alpha, beta, gamma, and delta, correspond to the elements on your vector, on your data vector. Okay, and there are other ways more complicated to do it. You can write down these expressions. There are several papers where they build this type of non-trivial encodings, and they can measure that, okay, this representation is better than this other one. They can do this with, like, for example, if your qubit is, how can I put this? So if you have more features than qubits, so that means your vectors are bigger than the amount of qubits. Today, there are no methods of putting that data inside a quantum computer. This is still an open problem.
That's gonna be a problem with you. Yes.
Yeah, sure.
Oh, yeah, but no, but that's actually one of the things we want to do because there are no like real world data sets that we can try, but this is something we can try. So you have the data, you know what it means, and all of that. So we will get together. I will try to understand the data. What's the problem you're trying to make? I've read a lot of the documentation on and the literature on quantum machine learning. So the idea is to get the right approach to start working with this data. Okay, but yeah, the idea is we want to go big because that's where the research is right now. Yeah, so this kernel method actually helps you build. Okay, so anyone here have ever heard the word correlation? Yeah, okay. Now, these correlations can be also written down in terms of vectors, apparently. And you can write down correlation matrices. Okay, so when you write down this as a quantum circuit, your data, you put it in a quantum circuit, and you would like to see the correlation of that quantum state with another that corresponds to your data. You can build these two as matrices, as unitary matrices, like here in this circuit. So let's say you have one for your xj element in your data, and you have another one for the xi, and you can see the overlap between these two vectors, and you can compute this in the quantum computer. So this is something that it allows you to do. You can do these correlation matrices between your data representations. sorry, so that you can see how your data, it's like more or less distributed inside this high dimensional space, to see that if there's a separation, a clear separation, or how to tweak some parameters, because now you can put the parameters on top and train the parameters. So this is exactly the next part. So for doing classification, so for example, this data set, spatial data set, can someone give me a little bit of details? Like, what is it?
It depends. Could be an image, let's say.
Mm-hmm.
So usually, if, let's say an image patch could be like 64 per 64 pixels.
64 by 64?
Usually we have channels.
Mm-hmm. Of color?
Yes.
Like 3?
Like 3, but sometimes we have 12 or 16.
Ah, nice. Okay. No, that's beautiful. But because you have different lengths, wavelengths.
Not just RGB, but also infrared.
Yeah, sure, because you look at the spectrum, the whole spectrum of light. Ah.
Sometimes with just spectral data sets, you can get 12 bands.
Uh-huh. Ah, that's gonna be fun.
Yes.
Okay. And what do you try to do with the data?
Usually classification, let's say a land cover mapping, so take
Mm-hmm.
a patch and decide this is background, or this is forest,
Mm-hmm.
or this is
Yeah.
land cover mapping.
Mm-hmm.
So at the end, you get the map.
I see. Mhm.
That's a basic.
Mm-hmm. Okay. Have you tried classical machine learning?
Classical what?
Machine learning.
Oh, yes.
Deep neural networks.
Yeah, deep learning is pretty good at it.
Oh, yeah.
We get very good results segment.
Mm-hmm.
So you are segmenting different classes, your patches.
Mm-hmm.
You would directly cover.
Mm-hmm. Okay. So let's say in that problem, you will have 2 classes. Let's say I focus on forest and not forest.
Yeah, you can simplify.
Okay. And then you can look at all the others. And this is called binary classification.
Yeah.
Okay. So let's say we focus on something like that. And what we'd like to do, let's say I find a way to put all of this in 1 qubit of information. And I would like to decide based on the measurement of the qubit. Okay. Now, when I measure 0, this is going to correspond to 1 class. When I measure 1, this is going to correspond to the other class. Okay. And the classification is based not on the measurements, but on the expected value, because we would like to add more qubits. Okay. If we add more qubits, we're going to end up with a lot of different measurement outcomes. And this is not, I would like to say, non-sustainable, because you will not be able to save all these states, but you can compute the expected values. Okay. So, and the way you do it is going to depend on the sign of this expected value. The expected value is all the time between -1 and 1. And you will say, okay, if it's negative, it's 1 class. If it's positive, it's another class. But you can also put, like, for example, ranges inside between -1 and 1 and say, okay, between -1 and -1/2, that's 1 class. Between -1/2 and 0, it's another class. And you can get creative. Okay, so there are ways around this. We can try a lot of things. But if you do only like a binary classification, it will look like the sign of something, either positive or negative. And the observable, what would you like to do with the observable? Same thing as we did before. We put parameters and we train it. Because, so we have at least 4 observables that we can measure. So these are the C that I already told you, the X and the Y. And there's another one called the identity. And we can do something called in linear algebra, like a change of basis. So basically what this means is you look at it from different angles. Yeah, and this is something we will do in detail in the next week, how to do this with respect to the measurement. And what we do is we add another layer of parameterized gates that are going to be optimized for the optimal measurement. So we will not know the exact observable, but we'll be able to compute the expected value. Okay, and we optimize for the optimal measurement operator. So this looks like this. See this W theta. This is going to be like a circuit on top of this that looks like this. So here, oh, oops. I have to go all over it again. Sorry. There. Okay, so you have a circuit here with a lot of qubits. Now the U of X, this is a collection of gates that correspond on your data. So this is how you load your data into the qubit state. And on top of that, you put the W theta. Now, this does not depend on data. This depends on some parameters that you put there. And then you optimize the expected value with respect to these parameters. Okay. And this becomes what we call a hybrid loop. So this is a quantum classical loop. And you do it like this. So you build your, actually, let me go back here to this one. There, okay. So what you do here is you put your data there, you evaluate your circuit, you compute the expected value for some values of theta, and perform the measurements. Yeah. X is your data. Yeah.
So you have a first operator, which is an encoder. So it's taking your X and it's putting this information inside qubits, set of qubits.
Yeah.
And you can play on the amplitude and you can play on the phase, right?
Yeah.
Rotation also. Like
Yeah, you have to decide what kind of encoding you use, like before you even start.
So what's the capacity? Let's say if we have 16 per 16, one image 16 per 16 pixels. How many qubits I need to use if I want to use those?
Depends on which paper you look at. Yeah. So there are different techniques to build this. We'll get more into the details. Yeah.
Theoretical definition of the maximum capacity?
No. We can only measure dimensions in this case and degrees of freedom, but there's no such thing as capacity. Also, in deep learning, you don't have a notion of capacity. Because there's a notion in classical machine learning, but when you go to deep learning, everything you know about machine learning turns out to be not true anymore. So you don't know what's the capacity of an artificial neural network. It's the same thing here. You don't know what's happening.
Well, in practice, the capacity, two definitions of capacity. There is the ingest capacity, which is the size of the input layer of the neural network. How many real input I can get?
Yeah, like the input size.
So for a CNN, for example, that's the size of the first layer. It's a matrix. And it could be 224 per 224, for instance, for ImageNet. And then you have the learning capacity of the neural network, which is something to it's not established. There's one definition, it's called the VC capacity. But that
works for machine learning, but when you go to deep learning,
So after the W theta is something else. It's the circuit by itself. Is it related to the cost function on a computer?
Yeah.
And get your observable, you want to measure. Okay. Getting there.
Okay. What about the rest? But at least you understand like the whole story, yeah, or the pieces of some pieces of the story. Okay.
Potential, maybe the obstacles, like
there are more obstacles than potential, I will say.
I would be ready to beat them to do it.
Okay. Yeah, and so the thing about this optimization is two things. So the parameters, theta, that you need to vary, you have to do this actualization on a classical computer. But the circuit, if it has too many qubits, you have to do it on a quantum computer. You cannot do it on a classical computer. For example, this laptop can model up to 20 qubits at most, but it will take a lot of time depending on the size of the circuit. There are simulators of up to 32 qubits in the cloud that we can have access to. But if you want to use more qubits than 32, then we need real quantum computers.
Is there, let's say, is it scalable? Let's say if I simulate for 8 qubits, get a circuit, but there is a pattern in the circuit that is repeated. Then I assume that I just have to repeat the same pattern to extend my circuit.
There are ways, for example, we know about the rules of multiplying the quantum gates inside the circuit. So let's say you have a big circuit and you find patterns. Let's say, oh, I can simplify this, and I can simplify this, and I can simplify this, and you do this with something with another type of theory. Actually, the quantum computer already does this on before running it in the real quantum computer. So you do it classically and say, okay, this is the optimal circuit that I need to apply with the cancellations and all of that. You obtain the same result at the end, but the computation takes less. There are also other things that we have to consider. So, okay, but let me just finish this part. So what happens here is you end up with something that we call a quantum classical loop, because you do some things on the classical computer, then you send the circuit, then you need the results from the circuit to do again actualization of parameters, then you obtain a new parameters that gives you new circuits that you need to send. So you obtain a loop between a classical computer and a quantum computer. And this is what research is today in quantum computing. Okay, these hybrid loops. There are research in other areas, of course, but when you look at quantum machine learning, this is the focus. Okay, we're trying to do something that corresponds to, probably it can be like optimization tricks. Like in deep learning, what you do is you decrease the learning rate after a few rates, so that will give you a better fit of your data. This is almost never tried in quantum machine learning. That's something possibilities that we can get, like going deeper into what kind of optimizations we can do. And this is just classically. And on the quantum side, we can play around with the circuit, with how we encode the data. We can come up with new ways of encoding the data and explore them in terms of the optimization. So, and you can produce a plot like this one at the top that if you've been doing deep learning, this should be like, is the same thing. So you can measure the loss for your training set and your test set and see if you have generalization. So these two curves should be together. You measure the same things, but for your quantum model. Okay. So, and there's other type of challenges. So let me show you another thing here. Gonna stop this one. There. Okay, so I'm here in my account. You should all have an account here. If you don't, it's free on the quantum computing for IBM. Now, if I go here to these 9 points, I can go to compute resources. This is a list of the quantum computers and the simulators that you have access to. Here I have a list. So the first column is the name. The second column is the number of qubits that you have access to. So these ones are big machines, 127 qubits. I'm going to show you this one, IBM Kolkata, which has 27 qubits. I've been using this one for some experiments. And let's hope I can see the architecture of the chip. Because this is telling you where the chips are, where the qubits, physical qubits are located, and how are they connected. Now, the connections will give you restrictions of what kind of gates you can apply. So for example, you can apply any kind of 1 qubit gate, there to each one of the qubits. But for 2-qubit gates, you cannot apply, for example, control NOT between the 0 qubit and the 26th qubit, right? Because they're not like directly connected. You can do it in theory, but in practice, you will have like to take the state of the qubit 0 and teleport it all the way to the 25th qubit that is next to the 26th, then apply a CNOT, and then teleport the state of the 25th to the 0. Okay, so then this is called like hardware efficient ansatz. Okay, so if you want to do a hardware efficient ansatz, you have to be aware of the hardware that you're using, so that you don't do things like this. Because if you use stealth Qiskit, the language that we're going to be using, the package we're going to be using, entangle qubit 0 and qubit 26, it will do exactly this that I told you. So you have to take the 0 qubit all the way there, put it next to it, entangle it, then go back to the 0. This will waste computation because let me go to this table. Okay, table. So this on the first column, you have the number of the qubit in this layout that I showed you. T1 and T2, these are times that measure how long does the quantumness stays on your qubit. Okay, so remember this picture I showed you of the quantum computer that is this big golden thing that it's built just to make work the chip at the bottom. This doesn't work for a lot of time. So this actually works, for example, on qubit 0, you had 105 microseconds before you lose the quantum state. Okay, so that means you get your qubit in state 0, you apply an X gate, this becomes the 1 state, and you wait 105 microseconds, and this state is something else. It's not the 1 state. Okay, so you will not have control over your quantum computations if you take too long to apply your gates. Okay, so that's another challenge. So that's T1, T2. It's another kind of how the state of the qubit will evolve. It's have to do with the phase of the qubit. We have other measurements of the qubits that are useful for other type of experiments, like the ones in chemistry, I will say. Yeah, so and also qubits are not perfect. So actually, if you go over it, you can see that you have readout assignment error. You have, for example, look, this one. This is probability of measuring 0, given that you prepare the state 1. Okay, so this is, for example, over this. This is the probability of measuring the state 0 if you prepare the state 1. So you start with your qubit in state 0, you measure, you apply an X gate, and do you measure right away? With this probability, you will obtain the other state. Okay, and you can twist it like this. The next one is measuring probability of measuring 1 if you end up with 0. For this qubit is low. Okay, but if you move, probably get higher. Okay. So but the parameterized quantum circuits are built precisely to deal with this phenomenon, because the parameterization will not work on the exact quantum state, because the quantum state is what we call noisy. These are called noisy intermediate scale quantum computers. So you don't have a way to deal with the noise. There are techniques, but they're costly in terms of classical computation and quantum computation. So yeah.
You mentioned that theory values.
Yeah.
But is it useful to also measure the variance?
You can measure the variance too. Yeah.
Because you can get the value, but it's
Mhm.
the bracket is very large.
Yeah, no, you're right. But so there's a result in physics that has to do precisely with that. It's called the Heisenberg uncertainty principle.
Okay.
We can look at the details of that, because the variance will depend on the operations that you use and the observables that you're using. And this is this can get technical. It's very mathematical, but you can prove it. And but yeah, in principle, yes, but it depends. Yeah. So yeah, so the general story of variational quantum algorithms is when you vary your parameters, when you vary your parameters, you can explore this quantum state using the noise of the quantum computer. Okay, because you will not have access to the exact state, but you have access to the expected value from this from this quantum system. Okay, you don't know the specifics of the quantum system, like what's the actual state, but you will be able to do optimization on it anyways. Okay, so I hope we're all on the same page. Do you have any questions, comments?
There is a question from
Yes.
Teams asking if IBM quantum computers is it a real quantum computer or it simulates a quantum computer?
Yes, I can answer that. So if you go here in your IBM Quantum Experience account and you go to the top, you can see three menus here. So you have your resources. These are the quantum computers I have access to because I'm logged into my account. If I go to all resources, I'm going to have more computers there. So you can see here I have one with 137 qubits, another one with 65, but I don't have access to them. So it says you do not have access to this one. But you also have here all simulators. So I go to all simulators. Now, this is 5,000, but it's not general. So because look, it says Clifford simulator. Clifford is a type of gate. So you don't simulate all of the gates that you can apply. You just simulate some of them. Now, by doing mathematics on these specific gates, you can simulate up to 5,000 qubits. This will not support variational algorithms for us because for variational, what we want is the variation of the parameters allows us to explore more parts of the circuit. And this is not allowed with these Clifford gates. We have another one with 100 qubits. It's the same thing. You just restrict to a thing called a matrix product state. This is a clever mathematical way to write down some operations. This allows you to simulate up to 100 qubits. The other one is similar. So this is extended Clifford. So instead of just the Clifford, you add some more. But this decreases the number of qubits you can simulate. Okay, because it makes the math harder.
You have like all systems. In the end, those are like physical quantum computers.
Yeah, so these are just simulators. These are classical computers simulating qubits and quantum gates. Yeah, and these ones at the bottom, these simulate everything that is happening in the quantum computer. What these two simulators do is they build the matrices and the vectors, and they do all the operations. Okay, so this one that says state vector, this is saving the whole vector of your qubits. And you have 32 qubits. So that means you have a 2 to the 32 vector. How much is that? So 2 to the 32, it's 4,000 million. Okay, so 4 billions. Okay, so it's a vector of size 4 billion, and they simulate it. And the matrices are 4 billion by 4 billion. Okay, so you need a big computer to do this. Your resources. You have access to the simulators? No, these ones are quantum computers. So let me put here 40. These are all, well, I have the simulators here at the bottom, but all the others are quantum computers. But look at the number of qubits. So 555, 777, 16, 27, 27, 27, 127. Now, IBM is saying they have a 4033 quantum computer, but no one that I know has access to it. So I don't know if they're having problems with it or what. But that's actually what happened with this 127 qubits. Everyone wanted to use it, but it's very bad. Look, I'm going to look at the errors for this one. So read out assignment probability of measuring 0. Okay, this one is good. This one is good. 0.02. So that's 2%. Which one is worst? Oh, look at this one. 20% of the times, you don't get the right result. Just by applying one gate, 20% of the times. Now, this gives you more and more errors as you evolve in your operations. So you cannot keep track of the actual quantum state. That's a problem. Apparently, IBM Sherbrooke, it's good. Oh yeah, I have access to it, but not privileged access. So I might want to use it. Now here you have the coherence time, so T1 and T2. Now this one is 300. That's good. Let's go for Washington. This one is just 100. Okay.
So when you launch an experiment, the simulation on the real computer, how many measurements you need to execute to have something meaningful? Of course, it will depend on the size of the circuit. But
yes, the answer is you don't know. You have to try, but there is a limit. So if I go here to the bottom, you can see your access providers. Now I have some access here. The number of shots, it's the number of times you do experiments. So you have 100,000, for example, and the other things are for other type of experiments. So yeah, you can do up to 100,000. Yeah.
limited by a maximum.
Yeah, exactly. But for quantum machine learning, what it's advised right now is just measure a few qubits. So that means you don't need as many as 100,000. So if you're only measuring the first 3 qubits, for example, you just need enough to distinguish between 2 to the 3 states. So you don't need the 100,000. Yeah.
And what's the overhead, let's say? Because you said before, there's a coherency time where your state are coherent, that will change.
Yeah.
After.
It will change randomly, and you don't know.
You have like a time window to execute your experiment.
Yes, that's this T1 and T2.
So when you do 10,000 measurements,
Mm-hmm.
it may happen that okay, it's not coherent anymore, and you need to reset your circuit or something like that, and redo that.
Yeah. Actually, we have something. This is new. Actually, this is something we haven't tried.
Okay.
And it was actually something I was thinking on using specifically for this project, and it's middle circuit measurements.
Okay.
So what you do is you do some operations, you take time of this T1, T2. Before you lose that, you do a measurement. So you're actually measuring a quantum state. You will obtain something, and that qubit is going to collapse either to 0 or 1, and that will enter to another quantum gate.
Okay.
And
stage.
Yeah. And if you do this in a way to reduce the number of qubits, this is called a quantum convolutional neural network.
Yeah.
And it will do something. So the circuit will start reducing in size. And apparently this can be trained, but you still have the problem of how much data you can put in it. But there are things we can try. Yeah, definitely. Actually, me myself, I've been like trying different things, and yeah. So don't worry about the size of your data. I think we can do something.
Okay.
Yeah, but it's gonna be fun. Yeah, actually, you can see your place in the list. So here you have 4,630 jobs waiting on the line to be run on this computer. I've run 567 experiments. What else can you see?
So when you have
Not
the account from IBM, I guess you have some limitations in terms of.
Yeah. So in this queue, for example, you have a free account. Like anyone can go and get a free account. You will get to the not to the end of the queue, because this depends on how much you use it. So if you use it a lot, it will give you less. Your priority will decrease in this list, in this queue. But if you have privileged access, like we do at the Informatique Quantique, you can jump in this queue. And we have also reservation time, so we can reserve the quantum computer just for us for, I think, 8 hours for each computer a month. So we can run, we can fix the computer just for us and do this classical quantum loop. Because actually this is another thing we should try in the project is When you send a job in your computer, it goes through the cloud to the quantum computer. The quantum computer sends back the results, and it's waiting there until your computer does this computation of the parameters, and it sends the new circuit. Okay, so the quantum computer is idle, doing nothing, while this information is traveling through the cloud. But the IBM released something called the Qiskit runtime. What it means is they put a server next to the quantum computer. Now you send your code, and it runs on a cycle next to the quantum computer. So you don't have to deal with sending information through the cloud. And this is faster. Okay, so this is another thing we can try, because in when you do quantum machine learning, is basically quantum classical loops, these hybrid loops, and it's way faster if we do this, if we use this Qiskit runtime. Yeah, so a lot of technical things to take into account. So
the next time,
we'll do variational quantum algorithms for machine learning.
okay.
Yeah, we will look at the examples with I think up to 4 qubits. We'll start with the 1 qubit example. I'll tell you what's the block sphere. I told you that the qubits can be represented on a sphere, and there you have some angles with respect to some axes. I'm going to tell you how you do this, how the measurement works in terms of this block sphere. So that we can have an intuitive way of what we're measuring with this C or the X or the Y. It's going to depend on the orientation on this sphere. So we'll be delving more into the details of how this works and how we can use that to do machine learning. Yeah, and we'll start with very simple machine learning, just binary classification. Okay. Okay. Any more questions? Maybe online?
No questions.
No? Okay.
Thank you, Marco.
Yeah. Thanks to you. Thanks for your patience. Okay. So apparently, I can convert the slides to a PowerPoint and keep the animations. Yeah, I didn't know that was possible. I tried it like a year ago and it was not possible. Apparently now it is. So I'll do that, and I'll send you the PowerPoints so that you can have access to the animations too.
Yeah.
Okay.
Share it on the Google Drive. So that
Yeah.
everyone-
Yeah, cool.
Thanks.
Okay. Anything else? And if not, I think you all have my